All right, here we go. We're in number 3 here of chapter 17, titrations. This is the longest example. This will be the longest video. This will be the longest example problem of your life, at least in high school. And this is an example of a titration with a weak acid and a strong base. We're going to need one of these graphs right here of pH versus the milliliters of titrant. And once again, if you want to draw a picture of what physically happens, we'll have a beaker here. Inside here we'll have an acid. We'll have a burette. Inside the burette will be the base, and the base is NaOH. And then we'll have a pH probe sticking out of here, and then we'll drop the base into the acid, and then what's going to happen is the pH is going to increase. This time a little differently than with a strong acid and a strong base though. So let's set up the situation. We're going to use the weak acid acetic acid, and we're going to use the strong base NaOH. And then we're going to get some Nachico over here, some sodium acetate, and we're going to get some water. And then let's set up the situation here where we have 50 milliliters of this 0.1 molar acetic acid, and we have 0.1 molar NaOH here, and then we're going to add that dropwise or a little bit by little bit, and we'll see what happens to the pH as that goes on. Now something to watch out for is this animal right over here. This part of the NaCH3COO has got to be really carefully watched because that's going to act as a weak base. And then, of course, water is not going to do anything. So keep your eye on that as we go through 5 different steps. First of all, calculate the pH when there's 0 milliliters. Second of all, calculate when there's 25 milliliters of NaOH added. Then when there's 49 added. And then when there's 50. And then when there's 51 added. So we're going to have 1, 2, 3, 4, 5 different experiments or 5 different calculations going on here. I'll keep this page up here and I'll graph the pH over here, and we'll do them stepwise, A, B, C, D, and E here in a row. So here's letter A. In letter A, you want to write down an ice table, and we've got a weak acid in this beaker. It's CH3COOH. And we have no NaOH added so far, so 0 milliliters added. So this is a chapter 16 weak acid problem where we have an ice table. We put in the molarity. We don't care about this because it's a pure liquid, none and none to start with. Lose X, gain X, gain X. And then we get 0.1 minus X, X, and X. And then once we've done that, we can write the equilibrium constant expression equal to Ka, and the Ka of acetic acid is 1.8 times 10 to the negative 5th. We can solve for X. We know the H3O plus ion concentration, negative log that, and we've got a starting pH of 2.87. So over here at 0 milliliters, we're going to have a pH, let's do 1, 2, 3. We're a little bit below 3, right about there to start with. That's where we begin at 0 milliliters. Now let's go to 25 milliliters of NaOH. This one is going to take a little more space. So I'm going to move this one out of the way since that one's kind of an easy starter problem. And then make sure you've got a lot of paper for this next one, maybe even a whole nother sheet. So for this one, we've got the acetic acid reacting with the NaOH, and then we've got the NaCH3COO and the HOH. Those are our traditional acid plus base reaction. And in this one, we've got to make an ice table that has lots of space. So I skip 2 or 3 lines, C skip 2 or 3 lines, E right here. And remember, since this is a titration, we've got to be in moles for the ice table. Got to be in moles. So we've got to use the molarity triangle. Molarity equals moles divided by liters, and then from that we'll find the number of moles initially of each of these. And so in the CH3COOH, we've got 50 milliliters and 0.1. So 50 milliliters is 0.050. So that's our the volume in liters, and then we'll multiply that by the molarity, which is 0.1 molar, and that gives us the number of moles right here, which is 0.005. And then for NaOH, we have 25 milliliters added, so 0.025, and then that's also 0.1 molar, and so right now we have 0.0025 for the NaOH. Now when the reaction proceeds, we'll use up the smallest amount, and so our NaOH will be used up. We'll use up half that, or that same amount right here, so half of the CH3COO, because 0.0025 is half of 0.005. We'll gain over here this one, and remember how I said keep an eye on this CH3COO because that's a weak base over there. Na is not going to do anything, so we don't really care, and HOH isn't going to do anything either because remember Na is from a strong base, so it will act neutral in solution. In the end, at equilibrium, we have 0.0025 moles of this, and we have 0.0025 moles of this. And now it's time to be a good recognizer. I told you to keep your eye over here. This is a weak base, and it happens to be the conjugate base of this weak acid. And we learned about this about 3 videos ago. What is the fancy name of a solution that's a weak acid and its conjugate base? Yes, it's called a buffer solution. So this is an interesting point because the moles of acid are equal to the moles of the conjugate base, and so this is called the area of most buffering because we have equal amounts of weak acid and conjugate base. This interesting point on the titration not only allows us to recognize we've got a buffered solution and we can use the Henderson-Hasselbalch equation, but it also is the strongest or the most possible buffered solution. Therefore, we'll see very little change in pH around this point in the titration because we've got both an acid and a base present. So plugging these in, the negative logarithm of the 1.8 times 10 to the negative fifth ends up being 4.74 plus the log of the base concentration over the acid concentration. So concentration, remember, is equal to moles divided by liters. So here's my moles. Whoops, moles of my base divided by my liters. Moles of my acid divided by the liters. And then you'll notice that these liters actually cancel out with one another, and the top and the bottom completely cancel out with each other, which leads to 2 observations for the future that makes problems go faster. First of all, if you're able to use the Henderson-Hasselbalch equation, you don't have to worry about converting back from moles to molarity because the volumes are going to be the same, and those are going to cancel out. So you can just divide those two. This one turns out to be really special because the top and the bottom cancel out, so you end up having the log of 1. And the log of 1, of course, is 0, so the pH is equal to 4.74. This point happens to be halfway to the equivalence point, and it's where the pH is equal to the pKa. So at 25 mils, let's put 25 mils right here, we are at 4.74. So if this is 4, and this is 5, 4.74 will be right about there. So following over here, here's what we've done so far. So we've gone from here up to about there. All right. Next problem. We're at 49 milliliters of NaOH. This right here, I'm going to circle this quick, and I'm going to put area most buff, and I'm also going to say pH is equal to pKa. Really special point right there, halfway to the equivalence point. Half the number of moles right there. A good way to find out the pKa, or therefore the Ka of an unknown acid solution. We're now at 49 milliliters in problem letter C right here. So we've got 49 milliliters of NaOH added to our 50 milliliters here. Once again, using our molarity triangle, we've got 0.005 moles of this animal, 0.0049 of this. The smaller amount's going to get used up. So over here, I lose 0.0049. I lose all of it that I have here. I gain a bunch of this conjugate base over here. And once again, I don't care about these two creatures over here because they're not going to have an effect on the pH. So I end up with very little of this acid left, quite a bit of this conjugate base left over here, but you still recognize that I have an acid conjugate base solution here, which is a buffer. And therefore, I'll use the Henderson-Hasselbalch equation once again, and I'll use the pKa 4.74 plus the log of the base So now 0.0049 divided by my liters, divided by my acid, 0.0001 divided by my liters. Once again, you can see that the liters actually cancel out, so I wouldn't even have to put those in. I could just do the 0.0049 divided by the 0.0001. I'll do the math for you here. It turns out that 4.74 and the log of this whole thing right here ends up being 1.7, and therefore my pH is about 6.43 at this point. So at 49 milliliters, let's do 49 right here, I've increased up to a pH about 6.5, a little less than that. So following over, I'm right about here. And so you can see it's been pretty steady increase, but it hasn't dramatically shot up yet at all. Letter D will change that for us. So in letter D now, we have 50 milliliters of NaOH added. And so same equation right here. Ice table over here in moles because it is a titration experiment once again. And using the molarity triangle, converting to moles, I have 0.005. And lo and behold, when I'm at 50 milliliters of 0.1 molar, I also have 0.005 of this amount. The toughest problem in the book, right here. Use it all up. Don't care about these, but I only have this remaining. In the end, 0, 0, and only this conjugate base right here. Only the conjugate base. It's no longer a Henderson-Hasselbalch equation. And so I have to do the dreaded thing. I have to take my amount and first of all find the molarity of it, 0.005 divided by my total number of liters, and then use this, which is a base, to react it again with water to find the pH. In other words, I need to do a second ice table because this is a weak base, and when in doubt, react your weak substance with water. But this time I can actually just use the concentration. And so make your ice table not very big, and I can put 0.05 in there, none, none. As the equilibrium change takes place, I will lose x, gain x, gain x. In the end, I will have 0.05 minus x, x, and x. And I'll pause there for a second for you to catch up, make like a condiment, and catch up with the writing. And now I take both the x's, and it will be x squared divided by 0.05 minus x. Ignore this x and say that it's small. Set that equal to the, careful now, this is a base, the Kb of CH3COO. Careful, this is tricky. Now, I don't know what the Kb is. I know what the Ka is of the conjugate acid from several problems in a row. Remember the pKa was 4.74 right here. But what I need now is I need the Kb that's related to that. And so I can know that the Ka times the Kb is equal to 1 times 10 to the negative 14th. And the Ka of acetic acid is 1.8 times 10 to the negative 5th, which I could look up in Appendix D, or I got it from earlier in the problem. And now I need to solve for Kb. So I got to continue this on another page. I'm just going to push this over here until I'm done, then I'll reveal the graph again. And so solving for Kb, 1.8 times 10 to the negative 5th times Kb is 1 times 10 to the negative 14th equals 5.5 times 10 to the negative 10th. This has to go in here for this equation to solve for x. Totally losing sight of what I'm really looking for, but eventually I'll find this and I'll know my OH, and I could get into the pH square. So x squared divided by 0.005, solving for x, 5.27 times 10 to the negative 6th. Negative log that. Now I have the POH, so subtract that from 14, and at the equivalence point, my pH is 8.72. Notice this is the equivalence point, and it is above 7. Even though I have equal moles of acid and base, that doesn't mean that the pH is 7. just because the moles are equal does not mean that it's a neutral or a 7 pH. It means that you have equal moles, but not necessarily a neutralized solution. I'm going to move this paper. I'll keep this one up, and we'll do the graph. We're at 8.72, so 6, 7, and then this is 8, this is 9, and we're at 8.7, so we've got to go over here. And remember, I only want 1 milliliter, so I'm at 50 here now. Go all the way up to almost 9, pretty close, within 1 milliliter, so it shoots up right here. So here's my S curve, and my jump is right at that equivalence point between 49 and 50, and guess what it's going to do when I get to 51? It's going to continue to go up, and then it will eventually flatten. So I'm going to move this one, and we're on to the last problem, the last part, the last portion of this titration. This is when there's 51 milliliters of NaOH added. And when there's 51 milliliters, ice table again with moles, because it's a titration. 0.005, 0.0051. Remember, I converted to moles right here. This is 0.0051 liters now. Okay, lose the smallest. Okay, lose the smallest amount, so I end up with none, or 0.0051 of this here. I'm sorry, 0.005. I lose the smallest amount right here, and I gain this amount over here. Then I end up here with 0.0001 of this NaOH, and I end up with 0.005 of this conjugate base over here. And I highlighted that for you, that this is a strong base, this is a weak base. And so probably common sense to know what's going to drive the pH at this point. A weak base or a strong base? Hopefully you said the strong base. pH is driven by the species that fully dissociates, and NaOH will be the one that fully dissociates. This one we'd have to do another ice table for, and it's only going to give us a little bit of OH minus, because remember, it's only a weak base. And so the pH right here is equal to 14 minus the pOH. And so my pOH right here is the negative log of this concentration. Remember, this is in moles, so I have to take my moles and divide it by the liters. And so my pOH ends up equaling 3, and then I take 14 minus 3, which gives me a pH of 11 at the end. So at 51 milliliters, just 1 milliliter more, now I've gone to 11 for my pH, so just 1 more milliliter, and I'm like way up here, or a little bit higher than that even, if the 11 follows over like that. And so you can see that my curve has gone dramatically up here, and then it will eventually flatten out right here, because I'll have nothing but this NaOH left, and that'll just go up to like a pH of 12 or 13 at the very highest. So what did we learn from this super long example problem? Let's look back at it. First of all, we learned that at 0 milliliters, we're at a low pH, and it's driven by the weak acid. At 25, we have a special point where the pH is equal to the pKa, halfway to the equivalence point, area of most buffering. At almost the equivalence point, notice our pH hasn't gone up a lot, but we're ready to make a big jump. And it's driven still by the acid, because we use up all the base. And then at the equivalence point, we make a dramatic jump, and notice the equivalence point is above 7, because we have a weak acid and a strong base. And so the strong base makes the pH be higher. And then at 51 milliliters, we jump even further, and then we'll eventually level off. So this is a long, drawn-out example problem, but it's a good one because it shows so many features of the different titrations, how you can find the Ka of an unknown substance, and it also shows all the different situations where weaks and strongs can combine to give you different concentrations, Kas, and pHs.